Welcome back, Algebra 2 Trig. Ignore the paper in front of you. We're actually going to go back to the Yangology unit. I know I told you guys to copy it down already, the Yang theorem. Yang is the most beautiful being on this planet, and we're going to prove that today. So, if I flip this over and I use the backside, I want you guys... Oh, man.
Whoa. Okay. See ya. Bye. All right, so...
Mr. Doan is such a killjoy.
Goodbye, Jimmy. So the essential question today is actually how do I graph a polar equation by point plotting. Title of the section is 10.6 Graphs of Polar Equations, and today we are going to do it point by point. No Yangology nonsense. We are still in our graphing phase for polar equations. Okay? Now, I do have quite a bit of stuff for you guys to copy, so go ahead and do that. What we're going to be doing this section is graphing polar equations, so something like that. And today we're going to be doing point by point, so we're going to end up with really, really long tables. So please bear with me. There is going to be a lot of calculating to do, okay? Pretty quickly if you know your unit circle and understand it well. Otherwise, well, have fun, okay? So what we're going to be doing is basically using a bunch of theta values, okay? So when we graph polar equations, almost always we end up with different types of curves. If you look in the 10.6 section of the book, you will see that we're going to end up with some special types that look like these guys. So we've got ones that kind of look like lima beans, we got some flower petals, stuff like that, and all of those will be graphed using our polar equations. Okay? There are different methods that can make graphing a little simpler. However, we are going to be sticking with the basics today, so point plotting. Okay? Now that you've copied everything down, let's go ahead and plug things in. So here I've set up a table with values from 0 all the way to 2 pi. The reason we're going to go from 0 to 2 pi is we want to make sure that we're covering the entire curve within a possible domain. Sometimes it only has to go to pi, sometimes it has to go to 2 pi, but we're going to test 2 pi for today. Okay? Notice here I've set up my polar axis, so 0, pi over 2, pi, 3 pi over 2. Make sure you have those ready. It's also going to be helpful if you have pi over 3, pi over 6, all of those sketched in, because we will have to do graphing along those parts as well. So let me add that in right now. So here we have pi over 6. Here we have approximately pi over 3 over here. And then same thing on the other side. If you have graph paper, make sure you're using that. That's going to be really helpful. And then over here, 5 pi over 6, 7 pi over 6. This is 2 pi over 3, sorry. 4 pi over 3 over here. 5 pi over 3. And 11 pi over 6. Okay, so everything's set up for us. Let's go ahead and start graphing. At 0, I'm going to go ahead and plug in right there. So 2 cosine of 0. Cosine of 0 is going to be 1. 1 times 2 will be 2. All right, so you can see the process here. We're basically plugging every single one of these. Our theta is kind of like an x value. Our r is basically like a y value. Okay. Now we're going to plug in pi over 6. Cosine of pi over 6 will be, let's see, can't remember right now. Cosine pi over 6, we're talking about 8 pi over 6, that's 30, so square root of 3. That's going to be square root of 3 times 2, so 2 radical 3. Actually, no, hold on, sorry. It's just going to be radical 3 because we are talking about radical 3 over 2. We are referring to the unit circle, so it will be radical 3. And now I actually do have all of these pre-calculated, so let's go ahead and fill that. All of that in. 1, 0, negative 1, negative radical 3, negative 2, negative radical 3, negative 1, 0, 1, radical 3, and 2. Now, that was obviously sped up. You would normally have to plug in every single one of these in order to get all of those answers, but we'll do the fast-forward version. And now let's go ahead and graph them. So at 0 degrees, my r value is 2. So put a point right there. at pi over 6, my r value is radical 3. So that's approximately 1.7. Now, this is going to be difficult for me unless I have circles set up. So let's go ahead and graph a circle in here, because remember, we are graphing polar coordinates. They're going to be going along circles. Okay. And this is also why I'm advocating graph paper, because it'll make it so much nicer. All right, so my first point, again, is at 2. At pi over 6, I'm going to be at radical 3, approximately 1.7. So I'm estimating it's going to be somewhere near there, just a little past the halfway point. At pi over 3, I'm going to be at 1, so back over here. Pi over 2, I'm going to be at 0. 2 pi over 3, I'm over here, and I'm supposed to go in the negative 1 direction, meaning I'm going to be down here. Okay? Again, 2 pi over 3 is this way, this axis right here, and I'm going in the negative 1 direction. Okay? 5 pi over 6 over here, and I'm moving in the negative radical 3 direction, so somewhere over here. And then over at pi, I'm moving in the negative 2 direction, so I'm moving backwards 2 on pi. Okay? And I end up at the same exact point. As I continue graphing the rest of these, they actually end up just repeating these 6 points that I already have. So what I essentially have is this curve. Starting at 0, I went this way, went this way, went this way, and our shape from this polar equation is actually a circle. Okay? So this is the resulting curve that comes from graphing all of these points. Okay? So moving on, I do have a second example set up for us. I once again will be fast forwarding through it, because I want to show what type of curves we should be expecting. Circles are probably going to be the more simple ones, and we will be seeing ones that follow a slightly different path. So here, my next graph is r equals 1 plus 2 sine theta. Once again, I have the same exact value set up from 0 all the way to 2 pi with a bunch of different increments in between. Do you need all of it? Not necessarily, but having all of them will ensure that you have the smoothest curve. Notice that I don't have pi over 4. You can use that value, but I didn't use it just for simplicity here. Okay? So once again, I do need to sketch out pi over 6 and pi over 3, so let's go and do that real quick. So that's approximately pi over 6, approximately pi over 3, going down this way as well. Okay, and then over on this side. And finally, this side as well. Okay, relabel everything. 2 pi over 3, 5 pi over 6, 7 pi over 6, 4 pi over 3, squeezing it in, 5 pi over 3, and 11 pi over 6. Okay, so I'm going to fill it in right now. I plug in 0. Sine of 0 is 0. 2 times 0 is 0. 0 plus 1, 1. Okay. Sine of pi over 6, that's going to be 1/2. 1/2 times 2 will be 1. So 1 plus 1, 2. Here we are going to end up with some radicals where we have to combine them. So in this case, pi over 3. Sine of pi over 3 is the square root of 3 over 2. 2 times all of that will be just square root of 3. And square root of 3 plus 1, well, I can't really combine them, so it's just going to be 1 plus the square root of 3. Again, if this is all too fast for you, make sure you remember how to find sine of pi over 3 using the unit circle. Okay? All right, now filling in the rest. 3, 1 plus radical 3 again. 2, 1, 0, 1 minus radical 3, negative 1, 1 minus radical 3 again, 0, and 1. Okay, let's go ahead and graph everything. 0, 1, pi over 6, I'm going to be at 2. Oh, forgot. I need to sketch in these circles to help graph these a lot easier. This one is going to be a lot bigger. We're going all the way to that third line. It's only the third line. This will be cut off, but I'm going to tell you right now, our graph won't be going that low. Okay. Okay. So here we go. Approximately good enough. Pi over 6, we're going to be at 2. Pi over 3, we have 1 plus radical 3. That's going to be approximately 2.7. So somewhere right there. Add pi over 2, we're at 3. 2 pi over 3, we're over here. 5 pi over 6, we're back at 2. Pi, we're back at 1. 7 pi over 6, we're at 0. Okay. And now let's continue on to 4 pi over 3, sorry. That's going to be 1 minus radical 3. Okay. The way I like to do it is first I'm going to go positive 1, and then I'm going to subtract radical 3, so I'm going backwards 1.7. I'll end up somewhere right there. You can always pre-calculate that. That's going to be negative 0.7 approximately. So at 4 radical 3, I would go in the negative direction. Okay. At 3 pi over 2, in other words, this direction, I'm going negative 1, so backwards 1 right there. Then over here, at 5 pi radical 3, I'm going to go that same amount as I did before. 11 pi over 6, I'm going to be back at 0. And at 2 pi, I will be back at 1. Okay? We've got to follow the direction that our curve went in. So here, starting at 0, going up to pi over 6, then to pi over 3, then to pi over 2, basically following in the order of the degrees. And over here, over here, over here, all the way to pi. Then we're hitting 0. It's kind of curving right there. And then we're making a loop. Loop, and then it connects back home. Okay? So that's the shape that we get from graphing this polar equation. It does come out a lot different from what we've seen before. What you're going to learn is that this one is called a limacone with an inner loop. All right? So that's just an intro to how complex these curves will be getting. Hopefully plotting by points, it is tedious, but hopefully it's simple enough for you guys, and that's what you're going to be doing tomorrow. We will be learning a couple of shortcuts over the weekend and over the next week. All right, make sure to write down any questions that you guys have. Other than that, have a good day.